All right, welcome back to our second section in Chapter 10. It's about measuring arcs and angles. So if we had a circle, that's terrible, but whatever. If we had a circle, we have the center of the circle, and if we take any two radii, the two radii will create one Euclidean angle and one non-Euclidean reflex angle, unless it's a diameter. That's a special case, we'll get to that. I'm going to call that x degrees. And I'm going to name these points A, B, and C. So we have an angle of x degrees in circle B. That angle, angle ABC, is called a central angle. A central angle is any angle in a circle whose vertex is at the center of the circle. Now, if you look at the circle, there are 2 points on it, A and C, and that divides the circle into two parts. There's this smaller arc here, and then there's the larger arc on the opposite side. And now my circle's somehow worse. But we have those two arcs. That smaller arc, the smaller arc is the arc intercepted by angle ABC. That's called our intercepted or subtended arc. I'm going to use the term intercepted much more often. Okay? But I just want to let you know that subtended is sometimes used. But I'm going to primarily stick with intercepted. So the intercepted arc is the part of the circle that is interior to the arc, to the angle rather. So the intercepted arc is the part of the circle that is interior to the angle. And an arc is just a part of a circle. It can be any size. So this big red piece, that's also an arc. So this is still an arc. Not an arrow, an arc. There we go. So they're both arcs, but this is the one intercepted by the angle. This is not intercepted by the angle because that is not a Euclidean angle. So we're going to be working in terms of that Euclidean angle. Okay? So now, I'm going to set up the same situation. So we had our radii like that. We had our smaller arc like that, and our larger arc out here. Again, I apologize for how awful my circles look, but we're all just going to have to deal with it. So we have this. Now let's talk about how we can differentiate between these arcs. This smaller arc here, the arc that's intercepted by any central angle, such that the angle is not a straight angle, is called a minor arc. A minor arc we name using the endpoints of the arc. So this green piece, the two endpoints are A and C, and then we put an arc symbol over it. Okay? That little rainbow on top, the rainbow hat, is the arc symbol. So that's arc AC. That refers to the actual physical piece. Now, the measure of an arc is different than the actual arc itself. Just like the measure of an angle is different than the actual angle. The angle is the physical piece. The measure is the numerical value that coincides with it. When we talk about the measure of an arc, we use a similar notation to when we did the measure of an angle. So this means the measure of the arc. And what happens, the measure of the arc for a minor arc is equal to the measure of the angle, the central angle, that intercepts that arc. So measures of angles are measured in degrees. Measures of arcs are also measured in degrees. The measure of an arc is different than the arc length. We'll talk about arc length later. So that's a minor arc. The other arc is called a major arc. Makes sense, major, minor. But we can't name it with the endpoints because, well, we already have arc AC. Arc AC refers to that minor arc. So what we're going to need is we're going to need another point on the circle. You cannot define a major arc unless you have another point that it passes through. And I'm just going to call this point D because of the alphabet. So this major arc would be called arc ADC. Its endpoints are A and C, so A and C should be on the outside. It passes through D. It is the same thing as arc CDA. Likewise, arc AC could also be called arc CA. Just like with a segment, it doesn't matter which endpoint you start at and which endpoint you end at, because it's going to give you the same exact figure. So arc ADC is the same as arc CDA. Just like with the minor arc, to talk about the measure, we use an M. But this time, it's equal to the measure of this angle, this reflex angle there, but we don't have a way to name that in Euclidean geometry. So we have to express this as 360 minus the measure of angle ABC. Or 360 minus x. Based on the fact that the minor arc is intercepted by a Euclidean angle, that means the minor arc's measure has to be less than 180 degrees and greater than 0. A major arc, its intercepting angle is a non-Euclidean angle, so its measure has to be greater than 180 degrees but less than 360. Now those are two types of arcs in a circle. There's one other type, and it's a very specific, very special case. And that is when the intercepting angle, the central angle, is not less than 180. It is, in fact, 180 degrees. So I'm going to use our same points, A, B, and C. And these two arcs are called semicircles. Now, both of those semicircles will have a measure of 180 degrees. So this one will be 180 degrees. This one will be 180 degrees, but we can't just call it arc AC because there's two with the endpoint of A and C. So what we need is we need another point to differentiate between them. So I'll put a point D there, I'll put a point E here. But any two semicircles on the same circle are going to be the same, have the same measure rather. So arc ADC, its measure is going to equal arc AEC's measure. And it's going to be 180 degrees. So semicircles are a very special case, but we still have to name it with 3 letters. If you're naming it with 2 letters, it's a minor arc. And if it's a major or a semicircle, it needs to be named with 3 letters. I almost just said any questions, but you guys can't respond right away. So I feel a little silly. But let's say we had 2 circles. Those are some real good circles. Just kidding, they're terrible. If the radius of one circle is congruent to the radius of another circle, the 2 circles are congruent. And if a central angle of one circle is congruent to the central angle of another circle, the corresponding intercepted arcs are congruent as well. So corresponding parts of congruent circles are still congruent. There's not a CPCTC abbreviation for that, because we're not going to be doing proofs, so you're not going to need to justify it like that. But you still need to know that corresponding parts of congruent circles are congruent. Nope. Sorry, my cat's trying to get in frame. All right. So we've talked about the measure of an arc. But that's not the only way to find a numerical value that corresponds with an arc. Oh, crap. Drop my cap. I'll get that later. Oh, don't eat it. That was to my cat. That wasn't to any of you. Also, don't eat my marker caps. Yeah, I'm not restarting this video because that went a little off the rails. Whatever. So if we're talking about arc length, arc measure is equal to the measure of the angle that intercepts the arc. But arc length is talking about the distance from point A to C along the circle. So the distance from point A to C along the circle. Well, we have talked about distance along the circle. We talked about that early in the year when we talked about circles, and we talked about it last section. It's circumference, which is 2 pi r. So you should probably label r. So what's cool is that the arc length with respect to the circumference is proportional to the arc measure with respect to the measure of the full circle. And the measure of a full circle is 360 degrees. So the arc length to the circumference is equal to the arc measure to the full circle. And the arc measures are both measured in degrees, so those degrees would really divide off. So I'll just erase that. Essentially, the length is equal to the angle measure over 360, oops, don't want that degree symbol, over 2 pi r. Not over 2 pi r, times 2 pi r. I wrote it right and said it wrong. So this is our formula for arc length. All right. There's just one more piece of this section. And it harkens back to the very beginning of the year. If we have a circle, and we have 2 arcs on the circle, and those 2 arcs are adjacent, we can have an arc addition postulate. Which says that the measure of the 2 arcs, the 2 adjacent arcs, is equal to the measure of the larger arc they form. Now, there's not really a good way to put this, and it seems a little counterintuitive, I know, and I understand. But for our intents and purposes, if we want to talk about the length of these arcs, technically, it would be length of ABC of arc AB plus the length of BC would equal the length of AC. For our intents and purposes, if we are talking about arc length, I'm going to accept just the name of the arcs. If we are talking about arc measure, you need the M. If we're talking about arc measure, you need the M. If we're talking about arc length, you can just give the name of the arc. There's not really a symbol for it like there is for arc measure. And we can't just say the 2 endpoints like we do for segments, because that would just be the length of the chord from A to B. That's AB. So if you have 2 adjacent arcs on the same circle, the 2 arcs, their lengths add up to the length of the larger arc they form. Their measures add up to the measure of the larger arc they form. All right, I hope that makes sense. And hit me up with questions if you have them.